On Gabor frames and Pisot family substitution tilings. Gabor frames for L2RD, which find significance in the theory of quantization and signal analysis, depend on two things: some window function G from L2RD and some lattice lambda in R2D. It is already well known that a good window function are functions from the so-called modulation space M1RD. Hence, finding a good Gabor frame is essentially equivalent to finding a good lattice to discretize the window function. A lot has already been done for Gabor frames based on periodic lattices, so we deal with the aperiodic case. In particular, we consider aperiodic lattices called PST model sets. Loosely speaking, a PST model set lambda omega is the relatively dense and uniformly discrete set of control points resulting from choosing representative points from the tiles of some tiling based on a cut and project scheme for a Pisot family substitution tiling var rho. An example is based on the famous Penrose tiling obtained from the following substitution, with the PST model set being the set of vertices of the tiles in the Penrose tiling. Now, given a PST model set lambda omega and a fixed delta greater than 0, there exist finitely many disjoint translates lambda I of lambda omega whose union lambda bar has hole less than delta. Therefore, if G satisfies omega delta G is less than 1 for some delta, and we obtain the corresponding lambda bar for lambda omega with hole less than that delta, then the pair yields a Gabor frame for L2RD which is equal, up to phase factors, to the multi-window Gabor frame generated by the Gabor translates of G with respect to lambda omega. Finally, considering the continuous hull of lambda omega and general modulation spaces MPRD for P from 1 to infinity, it can be shown that the multi-window Gabor frame generated by the Gabor translates of G with respect to any lambda in the hull of lambda omega is also a frame for MPRD for all P from 1 to infinity. Thank you.
Good day everyone. In this presentation, we will talk about the quantum time of arrival for the harmonic oscillator using the simplest symmetrization rule. So to start, quantization is used to form quantum operators corresponding to classical observables. However, there is an infinite number of operators that correspond to the classical observable p to the m q to the n. And each choice of arrangement of products is known as an ordering rule. So we have the Weil, simplest symmetric, and the Born-Jordan. Now, the operators Smn in the simplest symmetrization rule are defined as equation 1. So, example, we have S02 equals q squared and S20 equals p squared. Now, the commutation relation is given by equation 2. So, to solve for the quantum time of arrival, we start with the canonical commutation relation given by equation 3. Now, recall the Hamiltonian given by equation 4. Next, we write the unknown time of arrival as a linear combination given by equation 5. Now we arrive at equation 6. Using the algebra of the basis operators Smn, we obtain equation 7. Now we can solve for the coefficients Amn given the following values. Now generalizing these yield to equation 8. Therefore, the time of arrival is given by equation 9. Next, we obtain the time kernel given by equation 10. We will use the generating function equation 11 to simplify it into equation 12. Now to conclude, first, we solve for the quantum time of arrival operator of the harmonic oscillator starting with the canonical commutation relation. Next, this was done using the basis operators Smn in the simplest symmetrization rule. Furthermore, results showed that the obtained time of arrival in the simplest symmetrization rule is equivalent to the time of arrival in the Weil quantization. And last, the resulting time kernels for these operators are equal regardless of the quantization used. That's it, and thank you very much.
Our presentation is about frame quantization and finite quantum systems. To start, given a Hilbert space H, a set F for some index set J is a frame for H if there are non-zero constants A and B such that this inequality is true. We note that if A is equal to B, then F is equal to tight frame, and when the index set J is finite, we call it a finite tight frame. Given a finite group G, and if there exists a unitary representation ρ, where ρ of G phi sub H is equal to phi sub GH for all group elements of G, then the frame is a group frame or a G frame. So if you have a finite frame F, expressed in Dirac notation, then the resolution of identity holds. Our goal is to construct tight group frames from unitary irreducible representations of a finite group, and this theorem helps us in doing so. If ρ is a unitary irreducible representation of G in H and a finite group frame is given, the recipe for the frame quantization that we are adapting due to the resolution of identity is given by 4. So for every complex valued function f, there is an associated while operator W sub f where D is the dimension of ρ. So the star product is the composition of two while operators given in 5. As an example, if we have this as our ingredients, then we have the tight group frame for L2 of D8. By letting ket of k equal to this, the while operator is given in 6, whose matrix entries are equivalent to this matrix. So when we compose two of these while operators, we get the star product given by this matrix. From these computations, we can solve for the quasi-probability distributions such as the P and Q functions. Using the fundamental Weil-Wigner formula for expected values, we have these quasi-probability distributions where they are found from the matrix elements in the star product computation. Thank you so much.
The Big Bang, though canonical, actually faces some problems, including why the universe is isotropic and homogeneous, and why the universe is flat. Inflation, a period of accelerated expansion in the past, explains away these problems. Chudhuri and collaborators proposed a novel mechanism of inflation by modifying the Friedmann equation. This equation tells how the universe expands given the energy density. Hinted by ideas in quantum gravity, they delayed this density term by Planck time. We studied this scheme and here present to you 3 insights. First, inflation is generic. Solving the delay equation involves several parameters, but for all the parameter values that we took, there's always inflation, confirming Chudhuri and the others' claim. But not only that, inflation naturally ends and asymptotes the usual Friedmann solution, a nice feature not found in standard theories of inflation. Second, larger density means larger universe. Though there are several parameters, the resulting expansion profiles can actually be traced to how they affect the energy density. And what we found is when they make the energy density larger, the universe also gets larger. Third, inflation lasts for one delay unit unless it's smaller than Planck time. We found, as the delay proponents did, that inflation lasts as long as the delay. But what we saw different is that when the delay is on the order of 1 Planck time or smaller, inflation can last much longer. So we posit that no delay is small enough that will bypass inflation. The delay scheme is still in its infancy. Nonetheless, it has interesting features, and we hope to uncover more for future work.
The similitude group, which is a combined elementary transformation of the plane, the dilations, rotations, and rigid translations, are the symmetries of the two-dimensional signals of finite energy, which are square integrable functions on the plane. In fact, the action of the symmetries is the unitary irreducible representation of this group, objects suitable in two-dimensional image processing and radar signal. The corresponding Lie algebra is generated by these matrices. This work exhibits the construction of the Lie algebra representation of this group. The co-adjoint orbit of the similitude group can be thought of as a cotangent bundle of a punctured Euclidean plane, where each point in the said plane has a corresponding tangent space associated to it, parametrized by these position and momentum variables. The Hamiltonian function is the dot product between the charts and the vectors of the Lie algebra. Then the Kirillov symplectic form that satisfies this equation is this two form. Therefore, this collection of differentiable functions are the classical observables defined on this system. On this space of observables, we introduce the Moyal star product defined by the matrix representation of the Kirillov symplectic form. This covariance property will deliver us the Lie algebra representation. The Fourier transform operators on the momentum space will give rise to this concrete computation, and by some change of variables, this expression is simplified into these operators, which defines our Lie algebra representation of the similitude group. From these operators, we recover the representations of the Euclidean motion group and the affine group.
Hello everyone, I'm Carlo and I'm going to be talking about the geodesics in the Ruppeiner geometry of an ideal gas. So first we ask, in a finite thermodynamic process, what is the path that produces the least entropy from state A to state B? And the answer is the geodesic with respect to the Ruppeiner metric. And in this study, we'll look at how this looks like for ideal gases. To start off, Ruppeiner showed that the Hessian of the entropy can be used as a metric on thermodynamic spaces, and Salomon and his colleagues showed that the geodesics in the symmetric produce minimum entropy yield. To make this more concrete, let's consider a thermodynamic space charted with these variables, and suppose we want to bring a system from state A to state B. If the process is perfectly quasi-static, we know that this produces no entropy, but to be more realistic, we proceed with a step-by-step process within a finite period of time. We then go to the high number of n limit, and in this limit, the curves become smooth, and of all the possible paths from A to B, it is the geodesic that yields the minimum entropy gain. So here are some samples of geodesics of ideal gas. Here, n is the number density and T is the temperature. For example, we want to go from state A to state B, then we'll have to walk along the red curve here. For processes with the same initial and final temperature, it is the isothermal process that minimizes the entropy production. If, however, states A and B seem to pass a divergence along the curve, then the actual geodesic path becomes this one. So the next thing we want to do is to look at how these curves will change for more complicated systems. For now, that's it. Thank you.
In this short presentation, I will be talking about deriving the so-called first law of black hole mechanics for charged black holes in Horndeski theories. With quantum processes at play, black holes are able to emit thermal particles, which we now call Hawking radiation. Radiation temperature and its entropy turn out to be just the event horizon's surface gravity and area, and the energy lost in the process could be expressed in terms of these parameters and changes in the black hole charges. We want to show that this first law holds in Horndeski theories. Because of the broad space describing these theories, we will work only in a small subclass together with a minimally coupled EM field. With this choice, gravitational waves travel at light speeds, and the event horizon remains as a spacetime's causal boundary. We looked at an example of these series where the solution may be written in this way, with f of r given by this expression. The solution turns out to be a known solution in general relativity. For this black hole, we can express the temperature and entropy in terms of the event horizon r plus, and from here we can write an expression for the first law. Aside from this, we can also look at the Smart relation, ordinarily given by this expression. It turns out that this does not hold for our solution due to the presence of a cosmological constant. Still, we may write a Smart relation by considering the cosmological constant parameter beta as a thermodynamic variable, with which we can define some sort of pressure and volume. And so with the first law, we also get the Smart relation given by the equation below. In future work, we wish to extend these results to the full Horndeski Lagrangian, and we would also like to explore the other laws of black hole mechanics. Here are my references. Thank you.
Good afternoon. I'm Natalie Lizar Rojas, and together with Dr. Eric Galapon, I present our paper entitled An Application of the Exactified PoincarÄ Asymptotic Expansion of the Hankel Integral to Thin Film Thermography. Introduction. The Hankel integral for an arbitrary function phi of x in the Schwarz space for arbitrary real nu and positive b is given by equation 1, where j nu of bx is the Bessel function of the first kind. In this paper, we solve for the Hankel integral that appears in solving for the surface temperature of semi-transparent polymer thin films given by equation 2, where psi of z are coefficients in terms of the characteristics of the film and r is the radial coordinate of the film. Here, we consider the asymptotic behavior of the Hankel integral as shown in equation 3, and use the distributional method due to McClure and Wong with the objective of obtaining accurate results that can exactify the value of the integral in equation 2, and capture the exponentially small terms in equation 4. For our results, we have obtained an exactified asymptotic expansion given by equation 5. The table shows that by the distributional method, the obtained asymptotic expansion gives better numerical accuracy than the power-type asymptotic series. In conclusion, an exactification of the Poincare asymptotic expansion of the Hankel integral appearing in the theory of thermal diffusivity of polymer thin films for arbitrarily large values of the asymptotic parameter B was obtained using the distributional approach due to McClure and Wong and the results of Galapon and Martinez. The exponentially small terms were recovered in the result, and thus we were able to obtain an exactified expansion of the integral. After which, we applied the result for small values of the parameter and found that the obtained asymptotic expansion is more accurate than its optimally truncated power-type asymptotic series. Thank you.